Howdy, this is your friendly neighborhood physics teacher here, and we're going to do our free response off of College Board for rotation. So again, so these questions come straight off of College Board on the your AP College Board questions, and we're going to work them, and here we go. So in their physics classroom, students want to hang a heavy sign of mass ms and length ls as shown in the figure above. I'm sure it's mass of the sign and length of the length of the sign. The sign makes an angle theta with the wall. Without any support, the sign would rotate clockwise while its pivot would remain connected to the wall. So all it's saying is it would rotate that way without, if it wasn't attached to anything, it would fall. The students can connect one support cable vertically from one of the hooks above the sign, as indicated by the dotted line in the diagram. So they can choose to pick any one of those. Rank the 3 hook locations according to the amount of tension that the support cable would experience if the student decided to support the side from that location. Use 1 for the least tension and 3 for the greatest tension. If 2 locations would have the same tension, give them the same number. Explain. So now the first thing we have to think about what torque is. So torque is just force times your radius, basically. On your equation chart, I think it does have it flipped, so I will put it, so RF, and your R has to be perpendicular to your force. So if we think about what R is just from the distance from your pivot point to whatever you're going. So that would be your R. In this case, our force is, wouldn't be going down. Sorry, we do have a force of gravity going down, but the force we're talking about is the force going up. That would be our force of tension. So think about relationship. So what happens to your R? What's happening to your R as you change positions? So your R is increasing. So if your R is increasing, so it's saying which is the least amount of tension. So if your R is increasing, how would that affect your force? What type of relationship is happening? Well, hopefully you're thinking that your force would decrease, which is right. So that is an inverse relationship. So it's an inverse relationship. So your least amount of tension would be C, and then B, and then A. Because the closer you are to the pivot point, the more force it takes to, in this case, hold up. You can do the exact same thing if you're sitting there on a door. So pick a really heavy door, and the reason the door handle is the furthest away from where the hinges are is because that gives you the most R. So pick a really heavy door and sit there and move your hand in, and you see that it takes more and more force to actually move that. You can see how more force it takes. So for this one, to get your points, you would have to talk about that. So you would need to put this, but you're also saying that your torque, you need to add that your torque that's causing it to rotate. So the torque's causing it to rotate would be your force of gravity of the sign. So the force A and force B and force C would have to counteract. So key points here to get points is you would need that you'd want the sum of your torques to be equal to 0. That means it's balanced. And so if you're looking at your torque, so the force of gravity is causing it to rotate. So that's the torque you have to counteract. So torque have to counteract. Okay, so that's the torque you have to counteract. And then also again, so you would want to use your torque equals, and they said go ahead, and I know I didn't put the sine theta in there, but since they gave you a theta, you would need to I should have added sine theta into that mix, but you're still just dealing with inverse relationships, so that you would also need to talk about to get full credit. And then of course putting your 1, 2, and 3. You actually did get a point if you got that. So there you go. So question 2. The students hang a sign with a cable, but the cable breaks and the sign rotates clockwise. The diagram below shows the sign at 3 different times. So time 1, time 2. So basically, you have it set up like this. One of the string breaks, and so it starts to rotate. Indicate at which time, if any, the angular acceleration alpha, that should only be one alpha of the sign is greater, or whether it is the same at all times. So, a couple of things, and it says, explain your answer, of course. So, you would need to get full points. You need to talk about how alpha depends. Your alpha depends on your net torque, what's happening here. So, when it breaks, again, it's that force of gravity that's causing it to rotate. Causes rotation. So that force of gravity is what's causing it to rotate. And we have our tension equals RF sine theta. You have to think about what's affecting. The radius isn't changing, because if it's the force of gravity always just starts in the middle. So your radius is not changing. Your force is not changing. So the big thing that's changing is your sine. So what's happening to your theta? Your theta is decreasing. So as your theta decreases, your torque decreases. That is a direct relationship. And because that also equals I alpha, so if your torque decreases, your alpha is also going to decrease, again, due to the direct relationship happening there. So, kind of putting that into terms, so it's asking us to, so what does it say? So indicate at which time, if any, the angular acceleration of the sign is greatest. So the greatest angular acceleration would be the time that it just started. Because as theta goes down, your torque will go down. And as your torque goes down, your alpha will go down. So there we go. So, we got a second part. So show that alpha can be modeled with that lovely equation, and rotational inertia of the sign is that lovely equation. So basically they're asking us to derive those equations. So we have our net torque equals I alpha. And we know that also our net torque is equal to R F sine theta. So we know we can set those two equal to each other. So we can do I alpha equals F sine theta. But then again, this is where we're having to put, we can't just leave it like this, even though we have to put what each thing represents. So our R is actually going to be L2. So we go up here. Our R is all of that. But remember, when you have a long beam like that, your force always comes to the center, so it'll just be half. So our R ends up being half of your length. So put this over here as a little extra. R ends up being half your length. So we plug that in. We know that the force is our force of gravity and sine theta. Now, our I. This I would, you would have to be given this information. This is not something you'd have to memorize. But for a long beam, your I ends up being that equation. So you can literally just plug that in for make sure you label it as MS and LS. So we can literally just plug that in for I. So that would give us 1/2 MS LS squared equals alpha. We know that our force of gravity is just mg. Make sure we put that s there. So again, so it'd be 1/3. Looks like a half done it. 1/3 ms ls squared alpha equals L2 squared ms g sine theta. At this point in time, we can just start canceling. So we have m's on both sides. We have an L on this side. We have an L on that side. That should be LS. Sorry about that. I realized. Kept talking about don't forget your S's. I forgot them. And then we're going to, because we don't have enough room, we're going to bring it over here. So we get that we have 1/3 of L alpha equals 1/2 of G sine theta. We're trying to solve for alpha, so we're going to go ahead and divide both sides by L, and going to go ahead and multiply both sides by 3. So that causes that cancel. So we get that our alpha is G sine theta 3, over 2L. So the thing is, so this was on our formula chart. This is on our formula chart. This would need to be given to you. You would not have to remember that, which it is given to you right there. So yeah. And then you just kind of supplement. You just plug in and supplement. Simplify, not supplement. Whoa, simplify. Okay. So the next question. So the students want to describe the angular velocity omega of the sign as it rotates. And they pose the following equation. Regardless of whether or not this equation is correct, does this equation make physical sense? So they're not asking is the equation right or not. It's just asking does it make physical sense? So let's rewrite the equation here. So omega times time equals, we have 3g sine theta over 2ls times t. So that's basically what it's saying. It's saying that omega equals this relative to time. Does this make sense? And so it's talking about, so as describe the angular velocity as the sign as it rotates and the purpose of the equation. The issue with this equation is, okay, so let's think about what's staying constant. Okay, gravity is staying constant. Our length is staying constant. So as time increases, so it's showing as time increases, goes up, that would cause your omega to go up. And then your theta is changing. So it can be going up or down. Could be, and again, so that would affect your omega as well. But the issue here is this time right there. So it doesn't actually make sense. You can't spell doesn't, apparently. It doesn't make sense. And the big reason why it doesn't make sense is because the equation only really shows omega going up because of this time here. Yes, theta does make it go down, but not enough compared to this time. So it doesn't make sense because your omega is shown only to increase, which in fact it does both. So students attached a rotary motion sensor to the sign, recorded omega and theta, and create a graph of there. Okay, so create a graph. 4 students independently derived equation and proposed them to describe the motion of the sign. Which equation best matches? Which equation best matches the data? Okay. So this is a omega theta. So we have to have omega and theta. Oh, look, we have omega and theta in all of them. Good. Theta, gravity really doesn't. So we think about it. Gravity really shouldn't play a part in this because it's omega is just your radius times your velocity. So gravity really doesn't play a part in it. So it's just according if we're using sine or if we're using cosine. Because of the way it's drawn, it's actually going to end up being cosine. So yeah. Okay. So that is it for question 1. I'll go ahead and do question 2. Question 2 is not that long. So question 2. So a ramp of height h0 is placed on top of the table that has an edge that is a distance h0 above the ground. A student places a hoop of rotational inertia, IH, mass m0, and radius r0 at the top of the ramp, as shown in figure 1. So figure 1. So we have this lovely little circle there. The figure below represents the hoop as it travels along the ramp. Draw a free body diagram that shows the labels the forces, not components, exerted on the hoop. to clearly indicate at which point on the hoop each force is exerted. Draw each force as a distinguished arrow starting on and pointing away from the point at which the force is exerted. Note, draw the relative lengths, all the arrows as relative magnitude. So basically, length matters. So think about what's going on here. So, and the key thing what's different here is we usually radiate from the center, but it specifically asked for, let's see here, draw to clearly indicate which point the forces are exerted. So it's actually wanting us to draw from the point. So so we do have a normal force, right? So we would actually have to draw all the way down here to our normal force. Because that is sorry, apparently Santa came early. There's things that thing. Our roof is getting fixed, and I just forgot about that. Sorry, I just heard people on the roof, and I was like, "What's going on?" Okay, so we have normal force going up. We have force of gravity going straight down. Now you have to think about when you draw gravity going straight down. Gravity is affecting it from the center. So this is what gets so wonky. So wonky to making me do this. Okay, and so gravity would go straight down. Now, to know the exact length, so it would be 1, 2, 3, and it's 1, 2, 3. Sweet. So I did finally draw gravity big enough. Because it says make it relative. So that's force of gravity. Because force of normal and your force of gravity in the x should be equal. So if I drew my force of which I'm going to erase, if I drew my force of gravity in the y, it's 1, 2, 3 links. My force of normal is 3 links. So we're good there, but we're going to erase that because it doesn't say components. So force of normal coming on the ground, force of gravity going straight down, and then we do have a force of friction. And your force of friction comes from the surface, so you would again draw it from here, and it would be, okay, so if it's so we're going to say it's 2. Because it's 1, 2, 3. So it's got to be, we'll just say it's 1. So that is our force of friction. So there we go. Whew. So this one is a little bit more complicated because it wanted to actually where the forces were coming from. Force of normal is coming from the bottom, force of friction is coming from where they touch, and then your force of gravity is coming down. And then getting it pretty relative. The reason your force of friction is only 1 is because if you look again, if we drew our force of gravity in the x, which I'm going to erase, that's 3 links, and it is going to roll down, so it's just got to be smaller than that 3 links. That's why I said we could have made it 2, but I went ahead and made it 1. Whew, there we go. So question 2. After it is released from rest, the hoop rolls down the ramp, launching horizontally off the edge of the table, and lands on horizontal distance d from the edge of the table. The situation is repeated, but the hoop is replaced with a solid disk of rotation inertia. And it says your d, stating that your inertia of the disk is greater than your inertia of the hoop. Still has same mass, same radius as shown in figure 2. In a clear, concise paragraph length response, so this would be like your second one on your AP test, that may also contain figures and or equations. So I can use equations, figures, that's awesome. Predict which object, the hoop or the solid disk, if either, will travel a larger horizontal distance after each object is released from rest, rolling down the ramp and launched horizontally off the edge of the table. In your response, discuss the physical aspects of the hoop and the disk that are similar and different, and how those differences affect the horizontal distance. Okay. So I would start with things that are the same. So things that are the same is same mass, same height that's being dropped at. So therefore it has same potential energy, gravitational potential energy, and it has, I was talking about it had the same radius too. So same radius, and it's got to have it's going to end up having the same mechanical energy. So same gravitational, so therefore it has the same mechanical energy or total energy, because it's all starting at gravitational potential. Now, so those are all the same. So let's talk about what's different. And of course, you would do this in paragraph form, not listing like I'm doing. So the big thing that's different is going to be the bottom kinetic energy, because it's rotating, right? So some of this rotation, some of the kinetic energy is actually getting broken into two different types of kinetic energy. It's getting broken into just normal kinetic energy, which is 1/2 mv squared, and it's getting broken down to rotational kinetic energy, which is 1/2 I omega squared. So you do have two kinetic energies that it's getting broken down to. And since we stated above here that the initial, your I, a moment of inertia for a disk is greater than your moment of inertia for a hoop, that said that in the other thing, that means that your KE, or your K, is going to be greater. So if we think about, let's do our mechanical energy equation for, so this is for the hoop, okay? So mechanical energy equation for the hoop. So mechanical energy equals your gravitational, this is at the top, and then it'll be your kinetic plus your rotational kinetic. Same thing for the disk. So the same exact equation for the disk. So mechanical energy equals gravitational equals that plus this. But for your disk, this is increasing. So if this is increasing, but all this is staying the same, so if this increases, that means this has to decrease. So if this decreases, we'll break this down. So 1/2 mv squared. So if that decreases, that means your velocity's got to decrease. So your disk will actually be going slower. So your disk won't go as far. So slower. So not as far. Not as far. This one will end up going faster, and it will go further. So, didn't mean to shrink it that much, but hope that helps. If you have any questions, please don't be afraid to ask. Have a wonderful day. Bye.